My name is Bjorn. Some of you might know me from yesterday from the startup competition. So this is another talk. Now it's a little bit longer, 10 minutes instead of 2 minutes, which makes it a little more convenient. I'm going to present a studio project that we have at MIT. It's together with two colleagues, Katharina Kramer and Lukas Niebenwein. And it's about machine learning-based estimation of above-ground biomass to increase the transparency of reforestation or forest preservation efforts. And this is a picture of a hut in a forest conservation project that I was visiting last year in the summer. And there's a drone in the middle of the picture. If you squint your eyes, you can see it. Or you can follow this big sign that points out to the drone. So why do we care about this problem? We know that 9 to 15% of all greenhouse gas emissions in the world are from deforestation or forest degradation. Unfortunately, that number varies quite a lot because it's hard to measure. But rainforests are vitally important, not only because they sequester carbon, which is released when they burn and causes climate change, but also because they control soil erosion with their roots. They filter the local waterways. One of the most important reasons, for example, for a reforestation project in Brazil. They offer food and habitat for the local population, and they also contain immensely rich biodiversity. So, also, if we look at forests and we think about international climate change, we realize, well, global population has somewhat realized that we need to do something against climate change. So government and companies are investing into carbon offsetting solutions. And in carbon offsetting solutions, forests are one of the cheapest carbon sinks out there. And with 2 to 25% of the cost of, for example, carbon capture plants, there are these ginormous machines that have a filter. It rotates, it sucks air, and stores it in a bottle in the form of CO2 that you drink and then release again. But why, if forests are so cheap to sequester carbon, do we not see more investment into reforestation or forest conservation efforts? And this hypothesis here is that reforestation and conservation projects, they really lack the funding because of an international distrust. Because the current monitoring techniques, they're insufficient to monitor carbon offsets or control selective logging. In particular, I'm referring to the current two standards that are out there. We are either doing carbon estimates per foot, which is on the left, there's a picture of me in the forest taking a picture into the front and some colleagues before me, and we can see that if you're now about to count each tree that you can see, measure their diameter and their height, it's going to be pretty challenging. But people can actually do this, but it turns out that it's very expensive. I've been hearing from the Ministry of Agriculture that it costs about $300 per hectare. It is biased, it introduces human bias. It is hard to scale because you need experts that count the trees. And in some countries, it can even be corruptible. The other method which I've seen around is that carbon estimates, you can do them by satellite. However, if you use a satellite, for example, Landsat, you have a 30-meter resolution. Other satellites can give you down to 30-centimeter resolution if you're down to pay a lot. But they can have high uncertainties. They do not detect selective logging robustly. And they cannot distinguish agroforestry with an accuracy above 90%. And more overall, they cannot really detect the height of the trees in like a small area. And satellites also introduce a long lead times because they circle the Earth in like maybe 10 days. And in 50% of the cases, there's going to be clouds over the forest and you can't see anything. So there's no affordable and accurate solution out there to monitor small-scale reforestation or forest preservation projects. That's where our idea comes in. We would like to increase the investment into reforestation projects by letting local forest owners, more overall small or medium scale that have less than 1,000 hectares of forest, fly the drones over their forest. They already have access to drones, surprisingly. We then estimate the above-ground biomass and detect logging with machine learning-based algorithms. That then enables the certified selling of annual carbon credits that the certified selling of carbon credits that we can then forward to the forest owners, for example, $28 per hectare, for them to conserve or reforest their land. And this is based on a study by Seema Jayachandran, who has had the same model in Uganda, where they paid $28 per hectare to forest owners, and it reduced the rate of deforestation. And also Peru has a project called Reforestation, where they pay $10 per hectare for people not to deforest, but they can't measure selective logging. So how this algorithm works is, here we can see a picture of two locals that are starting a drone and fly it over the rainforest. This is actually the Instituto Geográfico Nacional de Peru, and they collect the patches of aerial imagery. We then take the patches of aerial imagery, and the algorithm does two things. One, it estimates the tree height from a photogrammetry approach, which gives you the distance from the drone to the canopy, which is subtracted from like a height from the satellite to the ground, and then you're left with the tree heights. We're evaluating the accuracy. It's not determined yet how good it will get. And the second thing is a tree species classification, where you use like a standard deep neural network, ResNet 52 or something like that, and you feed in the image on the one side, and you get in points where your trees are and the species of each tree. You can then use an allometric equation, which tells you, given tree species and height, the biomass of the tree, which strongly correlates with the carbon that's stored in the biomass. Now, from my perspective, as I'm a PhD in machine learning, I think this problem is very interesting, not only because the environmental challenging, but also because of the data science challenges. There is labeled forest data, which is very frequent for temperate forests in North America or Europe, but there's very little data on boreal or tropical forests, which are one of the most important forests to conserve in terms of biodiversity. And so you could think about something like transfer learning or semi-supervised, unsupervised learning to approach this task, or just collect a ginormous data set if you have a gazillion dollars. In the Amazon rainforest, 1.4% of all the trees, they're so-called hyperdominants, account for 50% of the species. So we have a huge data set bias, because we obviously still really care about those very rare tree species, because sometimes they're the most valuable, like the Shiwawaku I was pointing out in the previous picture. Forests are spatiotemporally correlated. If you have an algorithm, you can really augment that algorithm by telling if the forest is gone, it's probably not going to appear 10 days after again. And finally, algorithms, if you build them, need to be interpretable and trusted so that you can gain certificates for like an international carbon market. So far, we've done 2 pilots to map a conservation project in San Ramon, Peru, which created this map to the bottom left and established contact to this conservation project, WWF, Ministry of Agriculture, Ministry of Environment in Peru, and National Institute of Geographics, Do Good Robotics, and created this baseline algorithm I've shown. So surprises during the field test, I think these are kind of nice to show, is that locals already have access to drones. I thought I'm going into some remote area in the rainforest where nobody knows about technology, but really most of them have some friend of a friend that owns a drone, typically used for videography, and we could use them. We could use these drones to let them fly over their forests. There's unfortunately very limited reforestation projects. I heard a lot about them. They have a big media, but if you start trying to hunt them down, it's not that many. Really, way more is forest conservation projects. So we refocused to develop a algorithm that can determine the CO2 stored in forest conservation projects. Some people fear to fly drones because the drones are very expensive, and on the first day I was there and I wanted to create a map, and I got this funding to create the map, so I was very excited, and I fly the drone And I started, and after 5 minutes, I hear the drone zooming and buzzing in the air, and I can only see blurred pictures on my screen. I crashed the drone into the tree. But luckily, I got the drone out, and we could collect the real data set. So it's good. But I can understand why people fear flying their drones, especially if they have like an expensive drone, like for example a $30,000 drone. And finally, people are incredibly welcoming. We can see here a family on the very right. They invited me to stay at their house for like a week, feeded me through. And also on the very left, we can see that's another picture of Sandro explaining me something about drones that I didn't know yet. So they're not down. Open questions. I'm not sure yet which allometric equation we should use. If some of you has an idea, I'm happy to hear it. We're not sure how to solve the data challenges yet without collecting a ginormous data set. And the other 2 points. So finally, we want to restore the most important carbon sink by making reforestation more trustworthy, while securing jobs for locals, protecting water biocycles and biodiversity. Thank you, everybody, and I'm happy to answer any questions.
Time for maybe one question.
So I was just wondering, how are you planning to evaluate your algorithms against the ground truth? Like you mentioned that it's hard to kind of collect existing data by just going around and counting the trees. Like, do you have access to some kind of ground truth that you can evaluate against?
Yeah, so the real ground truth would be you take a tree and you chop it down, and then you chop it down even further, you let the whole tree dry in your lab, and then you put it on a wave, and then you get the carbon. But obviously that's intractable to do for every tree, and you would be left without forest. So the ground truth normally that we would take is a forest inventory that was collected by ground, like by foot. The problem with them is more that they're expensive. And for height, and another idea that we have is there's a person that has a very good data set of LiDAR imagery of whole Peru. If we could get access to that data set, then we could use that as ground truth for the height data.
Okay, let's thank the speaker.